Now we want to look at sections 1 and section 2 put together. Conservative vector fields and independence of path. Now, if we look at 3 examples here, right? Here's our vector field, 1/2 xy I plus 1/4 x squared j. And we have 3 paths, 0, 0 to 1, 1, 0, 0 to 1, 1, 0, 0 to 1, 1 on different paths, right? First path being y equals x. So if we let r be, if x is and y are the same, we get ti plus tj, going from 0 to 1, 1. So the derivative is I plus j dt, and 1/2 xy plus 1/2 x squared. And so work is going to be the integral from 0 to 1 of the dot product, 1/2 t squared times 1 plus 1/4 t squared times 1, right? Gives us 3/4 t squared dt. Evaluate it, we get 1/4. Second path is x is y squared. So we let x be t, y would be the square root of t from 0 to 1. Derivative would be t, or 1i, and 1/2 2 over 1 over 2 the square root of tj dt. So we take the dot product in place of x, y. Right? We're going to get 1/2 t to the 2/3 I plus 1/2 t squared j. Take their dot product. You end up with this, and you get 1/4. And if you let y equals x squared, we do it a third time, you'll see we get 1/4. So the work done, right, doesn't matter which path. Now, the partial derivative of this in relation to y is 1/2 x. Partial derivative of this in relation to x is 1/2 x. This is a conservative vector field. And in conservative vector field, no matter what path, we get the same result. And so that's our definition. When you have a piecewise smooth curve, and you r of x of ti, y of tj, t running from a to b, and f of xy is a conservative vector field, right? Proven as conservative. Then work done is, now if you're going from A to B, then XB, YB is the end point, XA, YA is the starting point. And so the work, conservative vector field, can be found by taking the potential function and evaluating at the end point and evaluating it at the start point, and subtract those, and you will have the value. You will have the value. So here's a vector field. We have a piecewise smooth function. I don't know what it is, but it's not actually nicely smooth. It's not even piecewise, but it's going from -1, 4 to 1, 2. Partial derivative of this in relationship to y is 2x. Partial derivative of the j component in relationship to x is 2x. This is conservative. Right? Back in an earlier section, we found that this is the potential function. So the work done is the value of the potential function at the end point, 1, 2, minus the value of the potential function at the start point. It's called the fundamental theorem of line integrals. Fundamental theorem of line integrals. And so what we found out is that if we have a continuous vector value function, and we are looking at this integral work, the answer is independent of the path if and only if the function is continuous. So the vector function is continuous, doesn't matter which path. Take the easiest path to find the result. Vector, value function, independent of path. So here is a theorem, and these statements all say the same thing. If you have a vector value function, it has continuous first partial derivatives, okay? And you have a piecewise smooth function. If the function is conservative, that means there's a potential function. Okay, we found out for the first function, the thing. If we're looking for work, okay, if the function is conservative, it's independent of path. If work is independent of path, that means the function is conservative. And the third thing is that work equals 0 on every closed curve if the function is conservative. Function conservative, work done is 0 on a closed curve. Down here, here's a closed curve. And I can figure out what the value is by substituting in and doing the work. So that is vector fields, that is conservative. And so again, back to what I said on the last video, that we are going to try to evaluate these things, these vector value fields, line integrals, surface integrals. We haven't gotten to surface integrals yet. But what we have said for line integrals is that if I have a path defined, smooth curve path, then I can evaluate this line integral by substituting in for x, y, and z, and substituting for ds, this arc length. If it is this integral, that's work, and we can do the substitution of it. What we learned in this video is that if it is a conservative vector field, then I can evaluate work by using the fundamental theorem of line integrals. We'll add other formulas along the line, but these two charts, okay, are the key to this entire chapter, with the exception of section 1, where we need to be able to find the curl and determine whether guys are conservative or not.